Hello, and welcome to lesson 35 of this introduction to calculus with Wolfram U. The topic for this lesson is L'Hopital's rule. So let's begin with a brief overview of the lesson. So let's say you had a continuous function like x squared, and I asked you to find the limit as x approaches 5. What you could simply do is to plug in the value 5 in the function expression, and you'd get back the correct answer, which is of course 25 in this case. But if the function has a point discontinuity, then this would not work. So for example, over here for g, there is an issue at 1 because the denominator becomes 0. So if you try and find a value at 1, then you get back an indeterminate answer. Now, of course, in this case, what you could do is to simplify the function algebraically, like I've done over here, and then things work just fine. So if I now plug in x equal to 1, I get back the limit of the function g when x goes to 1. But there are functions for which this will not work. So for example, you have h over here, which is log x minus 1 over x minus 2, and simplifying h makes no difference. So the question is, what do you do in such a case? Well, in such cases, you can apply something called L'Hopital's rule, and that is the theme for this lesson, L'Hopital's rule. Okay, so before going on to the rule itself, let's talk about so-called indeterminate forms. So let's say you have a function f, which is sine x, and g, which is x. Now, you try and work out the ratio f of 0 over g of 0, and you get back an indeterminate. So that's an indeterminacy of the form 0 over 0 because you have both the values are 0 at 0. But if you take the function h over here, then that's 2x minus 1 over 3x plus 2. And if you plug in x equal to infinity, you get back something like infinity over infinity. So that's again an indeterminacy. And next, if you take the function y over here, then at 0, you have a 0 times infinity from here. So that's an indeterminacy of the type 0 times infinity. So when you try and evaluate it, you get back indeterminate. And finally, if you take the function z, that's cosecant x minus cotangent x, and again at 0, you have infinity minus infinity. That's a problem. So when you try and evaluate it, you get back indeterminate. So the point is that you will have situations in which the system gives you back indeterminate, and then the question is, how do you find limits in such cases? So as I said early on, the way to do that is to find the limits using L'Hopital's rule. So L'Hopital's rule says that if you have a ratio f over g, and you want to work out the value of that limit as x approaches a, then what you do is you simply work out the limit of f prime x over g prime x at that value a, assuming of course that that limit exists. So you can reduce the problem to a problem of computing the limit of a quotient of derivatives. So for example, in our function from the introduction, you had log of x minus 1 over x minus 2 when x approaches 2. And you see over here that when you actually take derivative and take a ratio, things are much better. You can plug in x equal to 2 and you get back the answer 1. You can confirm the answer with limit and you do get back the same result 1. So L'Hopital's rule is a very powerful rule. It says if you need to find the value of the limit f over g, you simply find the derivatives of the numerator and denominator separately and then plug in the values if that works. Okay, so as an example of 0 over 0, let's go back to our ratio f over g, sine x over x. Now you see over here that individually you have 0 over 0, but then if you take derivatives, things get much better and you get back cosine x, which has a nice value at 0, namely it is 1. So the limit of f over g, sine x over x, is just 1. That's a very nice and important result. Okay, next, if you go on to infinity over infinity, like with the function h, then you have 2x plus 1 over 3x plus 2. So you work out the limits, and they are both infinity. But if you take derivatives and take a quotient, then you just get back 2/3. And so the limit of the function h is just 2/3. Next, go on to type 0 times infinity for the function y of x. Now, in this case, you don't really have f over g, so you write as exponential of 1 over x over 1 over x, take derivatives, and then if you plug in x equal to 0, you do get back the answer infinity from above. So that's the limit for y at 0 from above. And here's a plot which shows quite clearly that at 0, the function does approach infinity if you go from the right, if you go from above. Okay, so on to infinity minus infinity for the function z of x. Now in this case, what you do is you first of all simplify, write the cosecant as 1 over sine and cotangent as cosine over sine, and get back a ratio. If you work out those two limits separately, you get back 0 over 0. But then if you work them out in terms of derivatives, you get back tangent of x, which is just 0 at 0. So the answer for the limit is just 0. Okay, now in some cases you have to apply L'Hopital's rule more than once to get the answer. So for example, here's the function f defined to be e raised to x over 3x squared. If you try and apply L'Hopital's rule once at infinity, then you get back infinity over infinity again. That's again indeterminate. So what you do is you apply L'Hopital again, and now things look good because you get back infinity over 6, which is infinity. So the answer for the limit is infinity. So you can apply L'Hopital's rule repeatedly, but of course it's going to be more time consuming, more expensive to do so. Okay, now some more indeterminate forms. So we have infinity raised to 0 to begin with. Here's an example. So let's say you have x raised to 1 over x. So if you plug in x goes to infinity, you get infinity raised to 0. So that's an indeterminacy. But what you do in this case is you apply a logarithm. And when you do that, then you get back something which is going to be much more practical, because the law of logarithm says this is log x over x. So then what you do is you plug in the derivatives over here and you get back 1 over x. So when x approaches infinity, the answer is just 0. So log y is 0, which says that the limit is going to be just 1. So that's a plot of the function showing it approaches 1 as x approaches infinity. As another example, let's take 0 raised to 0. So when you take x raised to x and apply 0 to it, you get back 0 raised to 0. But then again, you think of it as being a logarithmic case, so apply logarithms and you get back x log x, like over here, but then write that as log x over 1 over x, apply L'Hopital, and you get back that when x is 0, the answer is 0, so the original limit is just going to be e raised to 0 equal to 1. And finally, let's take the case where you got 1 raised to infinity. So when you add pi over 2, this function becomes 1. Sine pi over 2 is 1, raised to tangent pi over 2 is infinity. So that's 1 raised to infinity. So again, you need to do some logarithmic work. So you say, let's take logarithms. You get log of sine x raised to tangent of x. Pull down the tangent of x. It's a power. Then apply L'Hopital, like before. And you plug in pi over 2 and things look better, so the answer is 0 for the logarithm, and so the actual limit is 1. Okay, that brings me to the end of the lesson. So basically, L'Hopital's rule is very useful when you have indeterminate forms of the type, let's say, 0 over 0 and infinity over infinity. But of course, if you've got something like 0 raised to infinity or other things, you can work too. So let's say with some algebraic manipulation, you can tackle the case where you have 0 times infinity and infinity minus infinity. And if you take logarithms, then you could also tackle the cases where you have infinity raised to 0, 0 raised to 0, and 1 raised to infinity. And of course, sometimes you will need to apply L'Hopital's rule multiple times to arrive at a suitable answer. So that's the end of this lesson, and the next lesson will talk about slope fields and Euler's method. But before you do that, do revise L'Hopital's rule. It's a very important rule, a very useful rule, and you surely will benefit a lot from a review. So I'll stop over here. Thank you very much.